Welcome to Understanding Genetic Algorithms, where we embark on a journey into the realm of evolutionary computation. We'll start this video with the theoretical foundation and then explore the areas of application of genetic algorithms. After that, we'll dive into the details of solving the problem of finding the optimal path for a delivery service. Genetic algorithms are optimization algorithms inspired by the principles of natural selection and evolution. At their core, genetic algorithms operate through mutation, crossover, and natural selection. Mutation involves making random changes to individuals in a population and exploring new areas of the solution space. Crossover allows genetic material from two individuals to combine, generating offspring with a mix of their traits. Natural selection, based on a fitness function, ensures that the fittest individuals are more likely to survive and reproduce. Let's explore some examples of genetic algorithm applications. In engineering, genetic algorithms are used to optimize designs, such as aerodynamic shapes or structural configurations. Their ability to explore a vast solution space and converge towards optimal solutions makes them ideal for complex design problems. Similarly, in finance, genetic algorithms are employed to optimize investment portfolios, balancing risk and return to achieve desired outcomes. Their adaptive nature allows them to adjust strategies based on changing market conditions, maximizing returns for investors. Another fascinating application of genetic algorithms is in artificial life simulations. By modeling populations of virtual organisms and subjecting them to evolutionary pressures, researchers can study emergent behaviors and evolutionary dynamics, shedding light on the principles underlying life itself. Now, let's apply genetic algorithms to a practical example, finding the optimal path for a delivery service. We start with a city map and delivery points scattered throughout. Random routes are drawn, each with its current length displayed. Now let's examine multiple routes for the same set of delivery points. Initially, we have 12 cities with their respective routes. Next, the algorithm evaluates the fitness of each route and selects the 3 shortest ones. These 3 routes become our leaders for the next generation. Through mutation, random changes are introduced to each leader's route. Mutation involves swapping random points along the routes with a given probability. This process introduces variations and explores new paths. Now let's introduce the concept of crossover. Each route is considered a genome, and crossing involves taking points from 2 routes to create offspring. If a point is already taken, the algorithm moves forward along the parent route's path to find the next available point, ensuring the validity of the offspring routes. With mutation and crossover, the algorithm iterates through multiple generations, continually improving the route's fitness and convergence towards the optimal solution. And there you have it, a comprehensive understanding of genetic algorithms and their applications, culminating in a practical demonstration of their effectiveness in solving real-world problems. Thank you for joining us on this educational journey. Until next time. Remember, genetic algorithms excel in scenarios where there's a complex solution space to explore and optimize. However, they may not always be the best choice for problems with well-defined analytical solutions or those requiring real-time computation. Use them wisely, and they'll be a powerful addition to your problem-solving toolkit.